Good afternoon. Welcome to Pangu 9 Internals in South Seas CDF with Tielei Wang and Hao Shu. Before we begin, a few brief notes. Stop by the business hall located in Bayside AB. The Black Hat Arsenal is on the Palm Foyer on level 3, and of course the Arsenal reception at 1700 hours. If you haven't picked up your merchandise, today is your last chance to visit the Black Hat Swag and Bookstore. Visit the Kali Linux Lab in Mandalay Bay, A. Thanks for putting your phone on vibrate. It makes it easier for the rest of us to ignore the ringing while you wait for your voicemail to pick up. And with that, we welcome our speakers.
Thank you. Thank you very much for coming to our talk. My name is Tielei Wang, and this is Hao Shu. We are from Team Pangu. So in this talk, we are going to introduce the vulnerabilities and the exploits we used in Pangu 9, which is the only publicly available jailbreak tool for iOS 9. And because Pangu 9 has multiple versions, today this talk mainly focuses on the initial one, which is for iOS 9.0. And okay, so this is the outline of the talk. At the beginning, I would like quickly go through the iOS security architecture. And remember, after our talk, there will be a talk from Apple, which will discuss more on iOS security. So please refer to that talk for more details on iOS security. And after that, I will give a quick overview on Pangu 9. I will explain how we designed the exploit chain. And after that, I will elaborate the Userland vulnerabilities and exploits, and how we will continue to introduce the kernel exploits. Especially, we will discuss how we patch the kernel in the existence of KPP, as known as Kernel Patching Protection, which is hardware-based kernel integrity protection mechanism. And the most beautiful part is how Pangu 9 achieves the persistent code signing bypass, and we will give the details of that part. And finally, we will conclude the talk and answer your questions. So a little bit more about us. So Team Pangu is a security research team based in Shanghai, China. The team, actually, we have like 7 members. We have very broad research interest. But the team is known for releasing jailbreak tools, and we already did that for 4 times, I think. And we regularly present our research at different conferences like Black Hat, Kansas West, and so on. At the same time, we also run a mobile security conference named MoSec and Shanghai. So you can check the website for more information. In January, Apple released a white paper to explain the iOS security architecture. And by design, I say it's very good. It has the secure booting chain, and iOS is also known for the mandatory code signing, which means only the code signed by Apple or by the certificate issued by Apple is able to run on the iOS device. And in terms of Sandbox, yes, it's also very restricted. Any app you downloaded from App Store, or if you were a developer, you create your own app, it will run in a very restricted container sandbox, has very limited access to the system. And in terms of exploit mitigation, iOS has both the kernel side and the Userland address layout randomization, and also the non-executable, not writable depth. And also for on 64-bit device, Apple applies both the hypervisor technology and secure enclave processor, a separate chip, to improve the security. Now, let's see how we design Pangu 9. And so just in case some people here have no idea about what jailbreak means. Okay, so jailbreak means how it's a process to remove the some software restrictions by iOS. Actually, we know there are a lot of security mechanisms we just described, like code signing, sandbox, and there's no root access to the, you don't have the root access to the file system, and so on. So basically, Jailbreak has to rely on kernel exploits to disable or to achieve the goal, because many such restrictions are enforced by the kernel. So in other words, one very important thing for Jailbreak is to do the kernel exploits. So with this goal in mind, we use this figure to demonstrate the trade-off between the difficulty of gaining kind of code execution privilege versus the amount of the kernel attack surface you gain. Let me explain the figure a little bit more. So let's say you are a developer. You create your own app. You run it on the iOS device. So your app will run as mobile in the container sandbox. So it's very easy for you to gain the code execution as mobile, but you will also get a very limited kernel attack surface. Because if your app runs in the container sandbox, you can only talk with very limited kernel extensions. That means many vulnerabilities are not reachable in the container. And assume if you are able to get code execution as root, and even be able to, you can specify the entitlement of the program, yes, you almost get the full kernel attack surface. But at the same time, it's very hard to achieve code execution as root. So for a long time, according to the vulnerabilities we had, we prefer to run our code after sandbox, even as mobile. So mobile or root is not a big issue. So if we are able to run our code after sandbox, we can exploit the kernel vulnerabilities we had. So that the two dots are our preferred. So in order to run code after sandbox, our initial idea in Pangu 7 is if we are able to set this kind of environment variable called div_ld insert libraries, somehow we are able to insert our own dynamic library into a system progress if we are able to launch that program. This environment variable is very similar to load preload one on Linux. So basically, it will tell the dynamic loader, so you should load this kind of libraries first before you run the program. So in Pangu 7, we use this trick to inject a library into TimeD. TimeD is a system process. And that library is signed by a kind of expired license. As a result, our library runs in the context of TimeD and continue to exploit the kernel. So it seems very easy, right? But since iOS 8, Apple made a big change. So to kill this kind of exploitation technique, Apple introduced a new security enforcement called TeamID Validation. So basically, TeamID validation's idea is this. When you load a library, the kernel will check who created the library. There is the ID information embedded in the library which is not changeable. And the kernel will check whether the ID of the main executable match the ID of the library. If the main executable is created by Apple, but the library created from a third party, in that case, the kernel won't allow the process to load that library. So basically, TeamID can prevent system services from loading the third-party libraries. And there is some exceptional case. When we reverse engineer the iOS kernel, we find when the kernel applies the TeamID validation, it checks a special entitlement called com.apple.private skip library validation. So by the name, you can guess what it's used for. So if the main executable has this entitlement, then it's allowed to load any library. So who has this entitlement? We grabbed the entitlement on iOS root file system, and yes, we found there's a program called AnyAgent. It's a network extension something, which happens to have this entitlement. So now things become easier. So what we did in Pangu 8 is we mount a developer disk image into the iOS device. So we have debug server. Debug server is designed for developers. So you create your program. You want to debug it on the iOS device. So you mount the debug image. Then the debug server is available. So what we did is we mount the debug. So when the debug server is available, we ask it to launch AnyAgent rather than the program we create. And at the same time, we specify the DVLD insert libraries environment variable. And so when AnyAgent launched, it loads our library. Our library continues to exploit the kernel vulnerabilities. Yes, we can win the game. But since iOS 8.3, there are more and more restrictions. In iOS 8.3, iOS starts to ignore the DVLD environment variables. If you check the source code of DVLD, or if you reverse engineer the binary, you will see that unless the main executable has this special entitlement called getTaskAllow, it won't use any DVLD environment variable. So we checked AnyAgent's entitlement. Unfortunately, AnyAgent doesn't have this entitlement. So even AnyAgent is allowed to load arbitrary library, we are not able to force it to load ours. So it's useless anymore. And now, what's a challenge for us for Pangu 9? So at that moment, the vulnerability we had cannot be exploitable inside the container. So we still need to inject a dynamic library into a system service. And on the kernel side, we noticed that since iOS 9, the KPP is enabled, kernel patching protection. So we need to bypass that. Now let's go through the Userland part. In this part, I will introduce two vulnerabilities. One lead to arbitrary file read and write as mobile through kind of inter-process communication channel. And the second one is arbitrary code execution after the sandbox. So if you guys went to our talk last year at Black Hat, you may remember that last year we already talked about the XPC security on iOS. XPC is a new kind of inter-process communication method on iOS. It was introduced in 2011 in iOS 5. Basically, the application can talk with some system services through the XPC channel. And this piece of code demonstrates how we write a server on the iOS. So basically, the first API is used to tell the system, hey, I'm running this server, and this is the name. And after that, you set up some event handler and message handler. Then you are ready to receive messages. And this is a demo for the client side. You still use the first API with different parameters. You tell the system, hey, I'm going to talk with this server. Please make the connection. And then you can build the XPC dictionary. This is the format of the message and send it to the server. So it's pretty easy. And last year, we talked about some vulnerabilities in the XPC service. And one of them is this one. So we found a vulnerability in asset D, which is services called com.app persistent URL translator.keeper. Anyway, so this services is related to the photo and some other things. And the program has a method which is invocable by any container application. So the method is supposed to move a file or a directory and the specified path to a new location under the where mobile media DCMI. So, but if you look at how the file move implemented, you will Don't laugh. Okay, so basically, from the XPC message, the program retrieves source path and the dest subdir. And then for the dest dir, there is some string operation. It's just put two strings together. Apparently, there's no any validation on the two strings. So it's very easy to use // trick to traverse the path. So far, this is a piece of the POC code. Use this piece of code, you are able to move or read anything you want. And so apparently, it's very easy to do arbitrary file read and write. You just move some file you want to read to your local directory, you can read it. And you can also move it back so you can write it. And the even good thing, the better thing is that services itself doesn't have any sandbox limitation. So arbitrary file read directly results in privacy leaks, right? So if you downloaded a malicious application from the App Store and the app that malicious app uses vulnerability, it can easily get your message, your photo, whatever you have in your phone. And arbitrary file writes even worse. If you guys are familiar with this talk, Mal airdrop by McDonald at RooksCon last year, that talk demonstrated how to transform a arbitrary file write into arbitrary app installation. So basically, if you can do arbitrary file write, you can install any app on the phone. And you can also replace the system app and do a lot of evil stuff. And one thing you need to emphasize that it's exploitable by any container application. So next, I will talk about how we transform that arbitrary file read and write vulnerability into arbitrary code execution. Recall that the DYLD insert libraries only works for the executables have the get task allow entitlement. So who has this entitlement? And we grabbed the string on the iOS file system. Unfortunately, on iOS 9, new program has this entitlement. So it's very bad. But we find a surprise in the developer disk images. In a very old version of the DDI, we found there is a program called AnyAgent, which happens have this entitlement. So now we try to mount the old version of DDI into iOS device so that we have the VPN agent available. And in the beginning, we found, no, the iOS 9 has a version check on the DDI. If the DDI developer disk image is too old, it refuses to mount it. We thought maybe we cannot do this. But later, after we reverse engineered the mobile storage mounter program, which is responsible for the mounting job, we found there is a logic error. So in each developer disk image, there is a file called trust cache, which contains sort of hash values of the executable in the developer image. So it's used to tell the iOS kernel who created the program. The programs are created by Apple so that you should run it without triggering any code signature failures. So what mobile storage mounter did is it loaded the trust cache first and then applied the version check. So even the old version DDI cannot be mounted successfully. Mobile storage mounter already registered the trust cache into the kernel. So VPN agent, the old VPN agent, is executable now. If you can run it, it won't trigger any code signature problem. So now we try to debug VPN agent. The trick we use just as we did last. So we mount a normal DDI. So we enable the debug server. And now we use the XPC vulnerability I just introduced. We move the VPN agent into some place where the debug server has access to, but the kernel doesn't apply the default sandbox. So here's the thing. So if the executable is under the private var mobile container date directory. By default, the kernel will apply the container sandbox. But if the main executable is not in this directory, the kernel doesn't apply that sandbox. So things is easy. But you may already notice that VPN agent does not have the com.apple.privateskip library validation entitlement. So even now the question is, even we are able to run VPN agent, and we can ask it to load our library, but we cannot bypass the TeamID validation, right? So there are two bonus of get task allow. It's a kind of logical conflict between debugging and code signing. So now assume you are debugging your own application on iOS. You want to set up breakpoints. So how breakpoint works? That means you need to change the instruction into some special one, and it will trigger the breakpoint. So that means code signing doesn't work. So why? Because the server will check, the iOS kernel will check if a program has get task allow entitlement, and the program is being debugged. That means it's a kind of debugging process. And in that case, even the code signature invalidation happens, the kernel won't kill the program. Rather, it will allow the program to continue to run. So now we have a way. So what we did is we just reuse the code signature of a system library in our dynamic library, so that when you load the library, the iOS kernel believes that you are trying to load a system library. So TeamID, okay. But when the library gets executed, it will trigger code signature invalidation error. But the kernel found, okay, now it's being debugged, and the process has a get task allow entitlement. So the kernel won't kill the program. And our dynamic library can continue to run and exploit the kernel. So put it all together, what we did is we first mount a old DDI so that we can make VPN agent be a platform binary. And we also mount a correct DDI so that debug server is available on iOS device. And we use the XPC vulnerability to move the VPN agent to some place where debug server have access. And now we debug this copy of the VPN agent and force it to load our dynamic library. And the dynamic library is kind of carefully designed so we can bypass code signing and TeamID validation. So yeah, now how we'll continue to introduce the kernel part and how achieve the persistent code signing bypass.
Hello. Thanks for today and talking about the Userland part, and I will introduce the rest part of our jailbreak. First of all, we will talk about the kernel exploit and the kernel patching in Pangu 9. We will not talk about the details of the patching, but we will tell you how to bypass the KPP. So to make a jailbreak, you have to attack iOS kernel, because a lot of enforcement are actually implemented in the kernel part. So you need to patch them out like the MFI and the Sandbox part. So usually the goal of the exploit and kernel vulnerability is to gain the arbitrary kernel reading and writing. And to achieve this, usually we need to defeat and exploit mitigations in iOS like KISR and SMAP. Also, there's a new challenge in iOS 9. It's the kernel patch protection. Apple add this to prevent hackers to patch their kernel. Yeah, we will see how we resolve this challenge. Due to the time of this talk, we will not give very details about all the kernel vulnerabilities used in our jailbreak. We will give a short description of those 3 kernel vulnerabilities. So the first one is we used in the iOS 9.0 jailbreak. It's actually an user-free bug in IO-hit family. It's actually very easy to find if you audit the source of the because IO-hit family is open source. So, but this bug actually is unreachable in container sandbox. That's why Tielei talk about the Userland part of our jailbreak to finally achieve the code execution in a less restrict sandbox. So we could check the kernel exploit in that sandbox. And actually, this is a very, very powerful bug. If you exploit in this in a correct way, you can just defeat all the mitigations just by one bug. So we can pwn the kernel by one bug. Also, we actually already discussed the details and the way to exploit this bug in the formal conference at RuxCon and the POC. If you missed the talk, you can check the address here. You can download the slide and for the details. And in this year, we upgrade our Jailbreak 2 to support iOS 9.1. And in this version, we use another kernel vulnerability. Actually, this one is reported to Apple by Ambia from Google Project Zero. And after the vulnerability is patched, he released a POC code on the Google Project Zero code Google. Yeah. And actually, this is a race condition bug in IO registry iterator. We noticed that this bug is very dangerous because it's reachable in container sandbox. That means any application you download from App Store or you install from the web, and they are able to exploit this bug. Also, this race condition bug, if you find a good way to exploit it, it's enough to defeat all the mitigations. That you can also pwn the kernel by this one single bug. And as we know, we talked to the Lockheed Hart. As we know, he's a career genius hacker, and he has his own private jailbreak, and he explored this bug in his private jailbreak. After Ambia posted the POC of this bug, we we took a look inside of this bug and do some analysis of this bug and post a blog about it. It's posted on our Pangu blog. You can check at this address. Okay, so another kernel vulnerability is used in the latest jailbreak we just released like last week or 10 days ago. Actually, when I'm preparing this slide, there's no CVE number. But surprisingly, this morning, Apple released iOS 9.3.4 to just fix this bug. And okay, so here's the CVE number. It's 2016 and 14.6.15.4. Okay. Actually, I think the test team of Apple should thank Black Hat to put our talk on the second day. So they have one more day to do the test. Okay. So this bug actually is a heap overflow bug in IO mobile firm buffer. IO mobile firm buffer is used to it's related to the display. It's store some mobile firm buffer for the display. So this user client actually is accessible in container sandbox. I think this is the reason why Apple was so eager to release a fix of this bug, because it's very dangerous. Any application can use this bug to exploit your devices. Also, this bug is a very, very good bug. If you exploit it in right way, you can just use this single bug to bypass all the mitigations and totally pwn the kernel. Actually, why we released the jailbreak for iOS 9.3.3 is mostly because this bug is fixed in iOS 10 beta 2. So that's interesting. That means the Apple internal security team already know the bug and they fix it in the iOS 10. but they didn't fix this very serious bug in the 9.3.3. I don't know why, but we pushed them to do that, I think, and that makes the devices more safe. Okay, so also because of the time of this talk, we will not get very details and exploit way of this bug. We will leave this in the future conference. Okay, so after the introduction of the kernel vulnerabilities, we will talk about the kernel patch, especially on how we defeat KPP in iOS 9. Actually, at that time, the kernel images are all encrypted, as we know from the iOS 10 beta. I don't know why, but Apple just didn't encrypt their kernel image anymore. So actually, you can reverse the KPP part because the kernel image is not encrypted in iOS 10. But at the time we released the jailbreak for iOS 9, we don't have the binary for the KPP. So the way we do is to do some black box test to find out the weakness of KPP. So as the result of our test, we concern first, what does KPP will protect? Okay, we realized that all the read memory and read and executable memory inside the kernel cache is protected by KPP. So if you modify any of this memory, and panic will be triggered. So that means Apple wants to protect all the kernel text code and all the const variables. Also, we found that the page tables of those protected memory are also protected by KPP. That means you cannot make the protection of the memory from Rx to RWX. If you make it writable, the KPP also will trigger the panic. We also want to know what does KPP not protect. That means for these memories, we could modify these memories without trigger the KPP. So actually, the RW memory, read and write memory inside the kernel is not protected by KPP. Also, all the heap kernel memory you allocated later is not protected by KPP. Okay, so we go deeper. That we took for example, we took a Sandbox extension as an example here. We examined the macro handle of it to see what we could still modify. Here's the output of the macro handle. We pay attention to the protection flags here. The text segment is obviously protected by KPP because it's marked RX, but all the data marked as RW is not protected by KPP. And among these data segments, there's a very interesting section called GOT, G-O-T. This actually is marked as RW. That means you can modify this area of memory. And what does this use for? Actually, this section is used to store all the stub function addresses. We'll talk this later. Okay, so actually for the first jailbreak we released, we tried to patch MFI and the Sandbox. As we all know, both MFI and the Sandbox are actually the mark policy extensions. That means they call the mark policy register to set up all the hooks, and they check the privilege in the hook functions. Okay, so all the hook functions pointers actually are stored in the structure called the mark policy configuration MPC operations. There's a long list of function pointers stored here. So you can guess what? Before iOS 9.2, actually Apple stored these function pointers in data BSS. So it's marked as RW. Yeah. So it's very easy to patch it, because if you want to get rid of the specific hook, you can just set the pointers to null to get rid of it. But Apple realized how we patch this kernel in our jailbreak, and so in iOS 9.2, Apple moved all this data to the text const. Okay, so another way we could defeat KPP, as we mentioned before, the got section actually is inside the data, which is marked as RW, and we can modify this. What's this used for? The stop function. For example, the MFI extension needs to know if the system is in debug mode. It needs to call the PE icon as debugger, and actually this function is exported by the XNU extension. It's not it cannot implement itself. So in this situation, it just called the function address stored in the stub. It actually points to the original address of the PE icon as debugger. But since it's RW, so we could easily modify the address of this function. That means we could point the PE icon as debugger to somewhere else, like it's return doesn't return 0 anymore, it return 1. So M4 will think, okay, so I now has a debugger attached. So this is another way to cheat the KPP, and actually in the latest jailbreak 9.3.3, we use this way to patch the sandbox and MFI. Okay, so we will talk about another way that we defeat KPP. KPP actually is used to prevent kernel patching if you want to make this patch persist. Yeah, because through our observed that usually the trigger of the KPP is very random, but it's usually triggered when the device is not busy, and it is from seconds to minutes. Sometimes it takes hours to trigger the panic. So that means if you don't need a persist patch, like you could just patch and restore it in a very small time window, like just in 1 second, I think it's enough to do a lot of things. And that's very, very safe. Okay, so after talk about the vulnerabilities and the way to defeat KPP, we will talk about how the Pangu 9 jailbreak achieve the persistent. Usually, the persistent is the hardest part for an untethered jailbreak. Because there's the attack surface of the persistent is not very large like other attack. So we took a look at the attack surface here. First of all, it's the DYLD. Actually, in past jailbreaks, most attacks are aimed to DYLD. DYLD is responsible for loading the dynamic libraries. So if you can find a vulnerability in this in DYLD, you can load arbitrary dynamic library. And another attack surface is attack kernel. Actually, the kernel is responsible for loading the main executable file, the dynamic linker, and also the DYLD shared cache. So if you could find a vulnerability in this part, yeah, you are able to do persistent on our device. And another interesting attack surface actually is used in, we just saw this in the jailbreak for iOS 5. There's a file parsing bug in Recon demo. But actually, this kind of bug is quite difficult to exploit because at that time, there's no ASLR. And if there's an ASLR in it, it will be quite difficult. So after taking a glance of all the attack surfaces, we found that actually the DYLD shared cache is never attacked before. So what we did was do the code auditing of this part of code. DYLD shared cache actually is mapped into all the processes on iOS devices. So it's only load once at first time the DYLD try to load it. Actually, the DYD will call shared region check NP to check if the shared cache is already mapped. If it's not, it will open the cache file and check it will read the handler of the cache file and to do some simple verification of the handler, like it's a valid shared cache file. And after that, it will generate a random slide for the cache. And finally, it will call the shared region map and slide NP to map the shared cache into memory. Since DYD is open source, we could check the source code easily. And we'll find that actually the function will trap into kernel. There's a syscall for 438 trap into kernel to finally map the shared cache. So let's take a look at the structure of shared cache handler. This is well defined in Xcode handler file. You can find this. At the beginning, there's the magic string, like it's DYD version 0 or something like that. And after that, there's a mapping offset. Mapping offset points to an array of cache mapping information. This structure is used to tell kernel how to map the file into memory, like from file offset and size and map to which virtual address, like that. And the image information, actually the image's offset points to an array of image information. Image information basically is used by the linker, the DYD, to know actually which library is mapped at which address. So he can locate the library. Anyway, this structure is very simple, and if you are lazy, you can just use J2. Actually supports to decode the handler of the shared cache. So let's move to the kernel part. The kernel part actually, what did is very, very simple. It's copying all the mapping informations. That's the mapping information we mentioned before, and did some very simple check, like if it's on root file system, if it's owned by root, and finally it will just map the file into memory according to the mapping informations. Oh, also, it will record the first mapping and take its address at the base of the whole shared cache. So if we record the process of loading the shared cache, we'll find there's no explicit code signature verification of the cache handler. Yes, although the cache handler is marked as RX, but actually it hasn't to be RX because you don't need to execute the code inside it. So here, so what we did is to put a fake handler which marked with R, which is read only. Okay, so after you control the handler, you can control the mapping. So this is two snapshots. The first one is the original shared cache, the mapping information of the original shared cache, and the second one is the one we patched in Pangu 9. And we noticed that the fake handler actually at the beginning it points at the end of the file. Actually append the fake handler at the end of file, which has no code signature, but that's fine because it's read-only memory. So kernel think, okay, read-only memory, no signature, it will just let it go. It's okay. And the interesting part is that after control the mappings, we need to find a way to abuse the MFID to accept all the code signatures. What did we do to achieve this? Actually, if you notice here, we split the last mapping actually into three mappings. That enables us to actually the second mappings points to the end of the file. We appended the fake data there. That means we could modify any data in the second mapping. So what did we modify? Actually, it's just 2 bytes. If we recall how MFID test if they can accept the code signature or not, it will actually use the MIS validate signature. this function is exported by libmiss.lib. So since we could modify the read-only memory, actually the export table is located in the read-only memory. So we just cheat libmiss.lib. We could point the MI's validated signature to some other functions inside the dilab. We find this structure. We found these instructions. It's just a return 0. So after patch the kernel cache, the MI's validated signature is always return 0. Then boom, the MFID is fucked up. Okay. So final is the conclusion, and actually we released 4 jailbreak tools in past few years, and we found that actually it becomes harder and harder to make a new jailbreak because Apple's security is doing better and better. I think the battle between the jailbreaks and the Apple actually forced them to make iOS more secure than we think. And we are happy to see that Apple released the update of 9.3.4 just for 1 bug. That means because in past usually they will not do that quick update of their OS. And that's why I think why Apple patched this so quickly is because this bug is inside can be triggered inside the container sandbox. So also the RPC bugs and the kernel bugs can exploitable by container apps impose a huge threat to iOS security, and Apples are taking them really seriously. So they want to patch it as soon as possible. Okay, so this is our talk. Thank you all.